everyone, welcome to part 1 of chapter 20. Today we're going to start our chapter on radioactivity and nuclear chemistry. So radioactivity is the emission of subatomic particles or really high energy electromagnetic radiation from the nucleus of certain atoms. Okay, so all of this stuff that we're doing with radioactivity and nuclear chemistry is from the nucleus, right? That's why we call it nuclear chemistry. And any atoms that emit radiation are going to be said to be radioactive. So this has a lot of applications, right? We use this radiation a lot in the real world, especially in medicine. We can use nuclear radiation for diagnosis and treatment of certain medical conditions, and we'll get into that a little bit more in a later lecture. Most of these radioactive emissions, though, can pass straight through many types of matter, like body tissues or, sometimes even lead, right? They're really penetrating. Naturally occurring radioactivity is used to estimate the age of fossils or rocks or ancient artifacts. Maybe you've heard of carbon dating, right? We can actually see how old something is based on the amount of carbon-14 that's left in our sample. And then radioactivity led to the discovery of nuclear fission, right, which we can use for electricity, and also nuclear weapons, which I'm sure you've studied in history classes. So we're going to look more at these topics of, medical applications and carbon dating and fission and fusion, all of that a little bit later. Right now, let's focus on what radioactivity is and what nuclear decay looks like. So first off, the discovery of radioactivity. So BECQUEREL was really interested in newly discovered X-rays, right? We've talked about X-rays a little bit previously in Chem 1 when we covered chapter 7. And so I'm going to jump just kind of right where we left off. So Antoine Becquerel, he thought there might be a connection between phosphorescence and X-rays. Okay, so phosphorescence is what happens if you expose something to light for a while and then, you take it in the dark and it still glows. The first thing that comes to mind is a glow-in-the-dark shirt, right? Like you might have it out, you're wearing it around, and then you go in the dark and it still glows. Okay, so this isn't like, you have a black light. This is your shirt is glowing on its own. Or, like here, this looks like a soccer ball that's glowing because it was exposed to light previously. So he thought there was going to be a connection between phosphorescence and X-rays because he knows that X-rays, right, give off radiation. So he thought maybe this phosphorescence was doing something the same thing. So he designed an experiment to figure out if phosphorescent minerals gave off X-rays. Okay, and the way that we detect X-rays, we will use a photographic plate, and if the photographic plate starts to darken or develop, then that's going to tell us that there's the presence of X-rays, right? Because we can't see them, so we'll have to use some other way of determining that they are present. So I know this is a lot of words, but his experiment is that he took some crystals of potassium uranyl sulfate, and we know that potassium uranyl sulfate is phosphorescent. So again, if you expose it to light and then you take it in the dark, it will glow green. So he took these phosphorescent crystals, and then he put them on top of a photographic plate, and he wrapped those crystals in a cloth. Okay, because we know that X-rays are penetrating and they have the ability to go through matter. So he said, okay, if these crystals are giving off stuff, we need it to go through the black cloth and we need it to darken the photographic plate because that will prove that there are X-rays, right? Because we know that X-rays do that. So he took his crystals out in sunlight and then he wrapped them in the black cloth and then he stuck them on his photographic plate and it got dark. Right? And the picture down in the bottom right, that's the photographic plate. It got dark, right? And he did it over and over again, right? Because we have to have replicate results. So he kept taking his crystals out, he'd wrap them in the black cloth, he'd stick them next to the photographic plate, and it got dark. And he's like, awesome, boom, X-rays, right? Things that are phosphorescent give off X-rays. And he actually published it and presented it and was really proud of his work. Later, though, he discovered that photographic plate, right? He had, taken his crystals and he just kind of stuck them in a drawer because he was done with his experiment. So he stuck them in a drawer with a new photographic plate just because they happened to be there. But he hadn't exposed his crystals to light, so nothing should happen, right? Because he said that if it were due to X-rays, then he didn't expose them to light, so they couldn't be producing it because, we were looking for phosphorescence. We had to put energy in to get energy out. So long story short, what happened? In that drawer, even though the crystals hadn't been exposed to light, that photographic plate got dark. Okay, so somehow he's getting energy out, right, without putting any energy in. Okay, he didn't expose the crystals to light, so they didn't have the chance to absorb any energy, yet the plate still got dark, which means that energy was being released. So he's like, well, all right, guess that's not what I thought it was, right? So something else is happening, okay? So he discovered that certain minerals were just constantly producing energy rays that could penetrate matter, right? They could still go through that black cloth and darken the photographic plate. So he figured out that all the minerals that produce these rays contained uranium. So there's something special about uranium, right? And again, the rays were produced even though that mineral hadn't been exposed to any sunlight. Okay, so we didn't put any energy in, we were just getting energy out. Anyway, so since they were all coming from uranium, he called them uranic rays because, like I said, they only came from uranium. So they're kind of like X-rays, except we didn't have to put any energy in. We're just getting energy out, and it turns out not to be related to phosphorescence. That was more just kind of a coincidence. Okay, so fast forward to Marie Curie. I'm sure you've heard of her. She is super cool, right? Marie Curie is one of the first women in France to pursue doctoral work, which is awesome. She ended up getting her PhD, and as part of her PhD project, right, her doctoral thesis, she was going to study uranic rays. And so the first thing she wanted to do was to see if there are any other elements other than uranium that were emitting these rays, right, these uranic rays. So she used an electroscope, and I'll explain that on the next slide, to detect where the uranic rays were coming from. So she kind of just held it over rocks, essentially, and we're trying to figure out, does anything else produce these rays? Do you? How about you, right? And she figured out that these rays were coming from specific elements, so kind of like uranium, but other elements as well. And so she ended up discovering a couple new elements. One of them is radium. And radium, that's what's in this picture down here. Radium is so radioactive that it will actually glow in the dark just by itself. And it produces really significant amounts of heat. It's just given off a lot of energy. It's really, really radioactive. And then she also discovered polonium, which she named for her homeland of Poland. But she said, okay, well, now it's not just uranium that does this, there's other ones. So we can't call it uranic rays because it's not just uranium, so she called it radioactivity. And she is really famous because she has not one, but 2 Nobel Prizes. And if that wasn't impressive enough, her Nobel Prizes are in 2 different fields. One is in chemistry and one is in physics, which is crazy, right? People, barely ever get 1, let alone 2, and definitely never in 2 different fields. So she is really, really awesome. She won the Nobel Prize in physics because she worked with Becquerel and her husband, Pierre Curie, and they were credited with the discovery of radioactivity, okay, with these uranic rays. And then she won the Nobel Prize in chemistry by herself because she discovered 2 new elements, which is super cool. Okay, so like I said, the electroscope. So the electroscope is used to detect radioactivity. And so what happens is we input some charge, right? Essentially, it doesn't matter specifically how, but we make these pieces of gold foil here charged. Okay, so here we have applied a positive charge to the pieces of gold foil. And since the gold foil, both pieces are positively charged, they will repel each other. And so they'll spread apart. So we can actually look and see, okay, the pieces of gold foil, they've been charged, they're apart. And that's what you would see inside the electroscope. And the way that this detects radioactivity, so radioactivity is called ionizing radiation, okay? And so one of the things that this radiation does, and one of the reasons it's so harmful, is that it will, start knocking electrons off of, cells in your body and other things. So if there is something that is radioactive present, it is, again, producing ionizing radiation, which is going and ionizing the air molecules. okay? So it's ionizing air, and when it does that, right, it will cause some of these electrons to be attracted to the pieces of the gold foil and will make them neutral, so then they no longer repel. So if we see the gold foil pieces spread apart, then that means there's no ionizing radiation present because nothing is ionizing the air and freeing up these electrons to lop onto the gold foil. But if there is ionizing radiation present, then the electrons will, add onto the gold foil, make them neutral, and then they will hang straight down. Okay, so they've been discharged. So essentially, this is what she was using to figure out, was there any other ionizing radiation present other than just uranium? Okay, so what is radioactivity, right? So Marie Curie focused her work on discovering different types of radioactive elements, right? So like I said, she discovered radium and polonium and was working a bit with uranium. But Rutherford, who we've talked about before, Rutherford and some other chemists focused on characterizing the radioactivity itself. What kind of radiation was being given off? So that's where we're going to now. But radioactivity in general is the release of these tiny high energy particles or gamma rays, right? Can be either one or both from an atom. And these particles are being ejected from the nucleus. So again, the reason we call this nuclear chemistry is because everything has to do with the nucleus. This is very different from most other types of chemistry that we've talked about in this class and in Chem 1 and any other chemistry class you've had, because normally we're not dealing with the nucleus, right? The protons are staying the same. Like aluminum is going to be aluminum in our reaction always, right? And it's always going to have its set number of protons, its set number of neutrons. But the thing that changes in normal chemical reactions are the electrons, right? Electrons are being gained or, lost or shared, right? But it's all about the electrons. In nuclear chemistry now, we are all about the nucleus, and we really don't care so much what the electrons are doing. Okay, so just a reminder about the nucleus. This should be a review. The nucleus has a very, very, very small volume compared to the volume of the atom as a whole. The electron cloud takes up a lot of the space in the atom, but the nucleus itself is very, very tiny in the middle. But all of the mass essentially is in the nucleus. So it's really, really dense because it has a lot of mass in a really small area. That nucleus is composed of protons and neutrons that are held super tightly together, really compact. And just as like a side note, the particles that make up the nucleus are called nucleons. So if you hear me refer to them as nucleons, I'm talking about both the protons and the neutrons. I didn't say, neutron wrong or nucleus wrong. That's what we call the particles in the nucleus. Okay, so again, this bit should be a review. So here's how we will write different isotopes. And you need to be really familiar with this for this lecture in particular, because we're going to use this to write chemical equations. Okay, when we are discussing nuclear properties, the nucleus is called the nuclide. Okay, and then less than 10% of known nuclides are non-radioactive. Most of them are actually called radionuclides because over time they will decompose, right? They will give off something. Okay, and we'll look and see what those somethings are as we go forward. But each nuclide is identified by a symbol that indicates the mass number and the atomic number. The mass number is going to always be the number on the top. We denote that as the letter A. And then the atomic number is going to be on the bottom. We'll use the letter Z. And then finally, the chemical symbol is always going to be on the right, and that's where you'll write, He for helium or whatever the case may be. And that would be the letter X in this one here. The number of neutrons, if you need to calculate the number of neutrons, you'll just subtract the atomic number from the mass number, and you'll get that. So I like to think of it's set up really well for subtraction, right? Atomic, our mass number minus our atomic number gives us our number of neutrons. So every atom of an element is going to have the same number of protons. So that's the atomic number Z. So again, when we were looking at this here, right? So we have A over Z gives us X. A over Z gives us X. So all of them, say aluminum or whatever, are all going to have the same number Z. That's going to tell us what our chemical symbol should be, okay? Because they're all of them, all of a certain element has the same number. And then atoms of the same element, though, can have different numbers of neutrons, which give us different isotopes. So the mass number on the top can be different for different different elements, or sorry, for different atoms of the same element. We call those isotopes. And we will identify isotopes by their mass number. So like we might say carbon 12, we might say carbon 14, right? And so if we're talking about those isotopes, these numbers are the mass numbers here. We don't need to say what the atomic number is because all atoms of carbon will always have 6 protons. So that's redundant. So we can write them like that, or we can write them, we can have C 12 and 6, or we can have C 14 and 6, but as you can see, both of them will have a 6 as their atomic number. Both will say C for carbon. The only thing that's changing is the number of neutrons, which changes the mass number on the top. All right, let's talk about types of radioactive decay. So Rutherford discovered 3 different types of rays. He did a lot of really good chemistry, but this is one of them. So the first one that we're going to talk about are alpha rays. So that's going to be the lowercase letter alpha there, that thing that kind of looks like a fish. Alpha rays have a charge of +2 and a mass of 4 AMUs. And they are actually going to be the same as what we now know as the helium nucleus. So if our helium just lost its 2 electrons, then it would be the same as an alpha ray. Okay, so the helium nucleus is essentially an alpha ray. And then beta rays, so we have the capital letter beta there. Beta rays have a charge of -1 and a negligible mass. So they're essentially like an electron. Okay, and so these are both particles that are going to be emitted from the nucleus. And then gamma ray is a little bit different. So gamma rays are just light energy. They're not a particle like alpha and beta particles. They're just energy that's being given off, and they'll actually usually accompany, an alpha decay or a beta decay. Also, some unstable nuclei, so these 2 were not looked at by Rutherford, they were by other people, but some unstable nuclei will emit positrons, which you may not have ever heard of, but they're essentially an electron, but they're positively charged. So they have a negligible mass, but instead of having a -1 charge, they have a +1 charge. And then some unstable nuclei can undergo what's called electron capture. So instead of giving off stuff like all of these other ones, right? Instead of giving off alpha rays, beta rays, or positrons, or even light, some can capture an electron. And what happens is an electron from one of the inner orbitals gets sucked into the nucleus, essentially. So we're going to look at all of these in a little more detail. Rutherford discovered that during the radioactive process, atoms of one element are changed into atoms of a different element. This is called transmutation. Okay, this breaks all of the rules that we have given you previously in chemistry, because I told you, essentially, like matter cannot be created or destroyed, right? If you have an atom of aluminum on, your reactants, you have to have an atom of aluminum on your products. Well, matter still can't be created or destroyed, but now we can go and change, that aluminum or that carbon or that nitrogen, right? It doesn't have to stay the same on either side of the reaction. That will be a nuclear reaction, right? We're changing the nucleus, we're changing the element, okay? And so for one element to change into another, the number of protons in our nucleus has to change. So like here in this picture, this is undergoing alpha decay. We're losing essentially a helium nucleus, okay? And so when that happens, we're losing 2 neutrons, but we're also losing 2 protons. So if we're losing 2 protons, that means our atomic number is changing, because our atomic number tells us the number of protons. So when we change the atomic number, we are changing what element it is, okay? So this should be like crazy, breaking all the rules. So, like I said, chemical reactions normally involve changes in the electronic structure of the atom. So we're changing the electrons, okay? Atoms gain, lose, share electrons, but no change in the nucleus is going to happen. But now, what we're doing right now, we're doing nuclear reactions. So we're changing the structure of the nucleus. Okay, so we're changing the number of protons, or we might change the number of neutrons. But when we change that number of protons, we are changing the element. Okay, so when we undergo radioactivity, our radioactive nuclei will spontaneously decompose into smaller nuclei. Okay, they typically don't get bigger, they get smaller, and they undergo radioactive decay. So anything that undergoes radioactive decay, we're going to say that they are unstable. And like I talked about a little bit earlier, right, Most of them are unstable. Most of them will undergo radioactive decay. It just may be a really, really, really slow process. Okay. Again, the decomposing involves the nuclide that's emitting a particle or energy or both, right? So the one that is undergoing the radioactive decay, we're going to call that the parent nuclide. That is what we are starting with, okay? And then after it undergoes the decay, we're going to call it the daughter nuclide, okay? It gets to be a girl. I don't really know why. So we're going from the parent to the daughter nuclide. So most, like I said, are going to be radioactive. It may be a really small process, but all nuclides with 84 or more protons are radioactive. Okay, so this is essentially things that are like lead or above. All right, so we describe nuclear processes with nuclear equations. Just like we describe a chemical process with a chemical equation, now we have a nuclear process with a nuclear equation. So a lot of the same rules apply, right? Just like before when you had to have, 3 moles of aluminum on the left and 3 moles of aluminum on the right to keep it balanced, you still have to keep things balanced. Our atomic numbers and our mass numbers have to be conserved. Okay, so this becomes essentially like a math equation. All of the numbers on the top have to add up, right? So like in our example here, I have 238 on the top for my mass, and then 234 plus 4 on the right for my mass. So that's also 238. So our sum of our mass numbers are equal. Same thing with our atomic numbers on the bottom. We have 92, then we have 90 plus 2 gives us 92, right? So those have to be equal. So our sum of our atomic numbers on both sides must be equal. So we're keeping track of all of our protons essentially on the bottom and our neutrons essentially on the top. Okay, and you can actually do this to predict what the daughter nuclide would be if you know the parent nuclide and the particle that's being emitted, because you know what all of them have to add up to, right? If we know, if we started with 238 and it lost 4, then that has to be 234. If we started with 92 and it lost 2, then it has to be 90, and that 90 will tell us that that's thorium. Okay. All right, let's go through this. All the different types of decay. So the first one is alpha decay. So alpha decay occurs when an unstable nucleus emits a particle that has 2 protons and 2 neutrons. And like I said, this is a helium nucleus essentially. So 2 protons, 2 neutrons. It is the most ionizing, but it's the least penetrating of the types of radioactivity. I think your book describes it as like a semi-truck, which I thought was really entertaining. But it's a good analogy, right? So it can carry a lot of ionizing power, essentially because it's really, really big. It has the potential to do a lot of damage. Okay, so this would be really harmful to you, right? If you were getting hit by alpha decay. So alpha decay is, like I said, very ionizing, which means it can start to ionize some of the biological molecules that are in your body. And when it does that, it kind of damages them. And a lot of times your body can go through and repair them and everything's going to be okay. But sometimes it can't. And that's where you get into things like cancer and other problems. Okay, so it's really ionizing because it's so massive, but luckily it's the least penetrating. If you just wear some clothes or even keep your skin on, you're going to be mostly protected from this alpha decay. The only way you'd really be in danger from alpha decay is if you ingested something, if you ate something that was undergoing alpha decay, and then it could be directly in contact with your biological molecules. Okay, so, but alpha decay in general, if you lose an alpha particle, that means the atomic number is going to decrease by 2, right? We went from 92 to 90 because we lost 2 of those protons. The mass number will decrease by 4 because you're losing the 2 protons and 2 neutrons for a total of 4. Okay, so we're losing 4 from our mass. It can only travel a few inches through the air. So like I said, unless you are, standing, like touching something that's undergoing alpha decay, then you're going to be okay. Just don't eat it, essentially. So here's a picture of our alpha decay. Again, we're losing an alpha particle, which is a helium nucleus. Beta decay is the loss of something that's essentially like an electron, right? It's going to have no mass, really. It's going to have a -1 charge, much like an electron. It's going to be moving really, really fast, and it's going to occur when an unstable nucleus emits an electron. read that sentence again. It occurs when an unstable nucleus emits an electron. What's wrong with that statement? There's no electrons in the nucleus, right? You're like, okay, the electrons, they exist in the electron cloud. We learned this, right? There are no electrons in the nucleus. So how is the nucleus emitting an electron? Well, what happens is that, here, I'll show this here. What happens is that our neutron turns into a proton, okay? We have a neutron. Our neutron emits an electron and turns into a proton. Okay, so this is going to change our atomic number because we're taking one of our neutrons and we're turning it into a proton. So like if we had 6 protons before and one of our neutrons turned into a proton, now we have 7 neutrons. So that changes, or sorry, 7 protons. So that changes our element, right? It's because anything with 6 protons is carbon, but anything with 7 protons is nitrogen. So beta decay is when we have an electron that's being emitted from the nucleus, okay? Which again, I think should strike you as very strange. This is about 10 times more penetrating than our alpha decay because it's so small, right? Electrons really tiny, especially compared to protons and neutrons. Those are much more massive than an electron. So it's a lot more penetrating, but only about half as ionizing because it's small. Okay, and again, I think your book talks about this as like a 4-car or a 4-door sedan, right? So it can get through more places than a semi, but you know, if it, I don't know, crashed into you, it's not going to do as much damage. When our atom loses a beta particle, the atomic number is going to increase by 1. And again, it's going to increase by 1 because we took that neutron and we turned it into a proton. So we're adding a proton to our nucleus, kind of, right? So our mass number stays the same because we didn't add or subtract any protons or neutrons, right? All we did was we changed a neutron into a proton. So we're just changing the atomic number by 1. Our beta decay, like I said, is more penetrating, but it can be stopped by things like aluminum foil or a block of wood or the walls of your house. So if you were worried about beta decay, maybe you'd want to wear one of those, tin foil hats on your head. I don't know, that should protect you. Or just, stay in your house or whatever the case may be. Okay, but here is our example down at the bottom. So we have, again, our radium is turning into actinium because we are taking one of our neutrons and turning it into a proton. So our atomic number is increasing by 1. Okay, gamma emission. So the last 2 we looked at were particles, right? We lost a helium nucleus, and then we lost essentially an electron because we turned a neutron into a proton. Gamma rays, though, are not particles. Okay, gamma rays are just high energy photons of light. These are electromagnetic radiation that's being released. Okay, so we don't change anything about the nucleus. It's going to have the same atomic number. It's going to have the same mass number, right? Nothing changes. We are just releasing some light. It's the least ionizing because it doesn't have any mass to it, right? There's only so much damage it can do. But it's the most penetrating because it's so much smaller. So if you were to protect yourself from gamma emission, you could just have about a meter thick of concrete, which, okay, think about a meter stick, right, that we use like in lab, big, huge meter stick. You'd have to have that much thick of concrete or several inches thick sheet of lead. So this gamma emission really can penetrate, but again, not as ionizing. Generally, when we see gamma emission, it's going to occur in conjunction with some other type of decay. It will occur in addition to alpha decay or in addition to beta decay. It doesn't typically occur on its own. It can, but it doesn't usually. So like here, our equation at the bottom is one we saw before with the alpha decay, but now we've included the gamma decay at the end. Okay, so when this reaction occurs, it also releases energy in the form of gamma radiation, but a lot of times we'll just leave it out of nuclear equations because it's really common. Most times when something undergoes decay, it's also going to release some gamma emission. Okay, so a lot of times we'll leave it off just to make our lives easier and shorter and things like that because it's assumed that it's also going to give off some electromagnetic radiation. So here's a picture of the penetrating ability of different radioactive rays. Again, alpha decay is going to be the most ionizing, but the least penetrating. Beta decay is kind of in the middle, and then gamma decay is very, very penetrating, but not very ionizing. All right, so we talked about two other ones before, so positron emission and electron capture. Positron emission has essentially a positively charged electron. It has a charge of +1, but it has a negligible mass. So positively charged electron, not a proton, positively charged electron. And it's called an antiparticle of an electron. If a positron and an electron met each other, they would essentially annihilate each other and release some gamma emission. They are the opposite of each other. They're really similar to beta particles in their ionizing and penetrating ability because they're essentially the same thing, they just have the opposite charge. When an atom loses a positron from the nucleus, the mass number remains the same because we're not changing the number of protons or neutrons or anything, but the atomic number decreases by 1. Okay, again, it's going to be the opposite of when we did beta decay. So in beta decay, we had a neutron that changed into a proton. Here we have the opposite. A positron, we're going to have that proton change back into a neutron. Okay, so everything about positron emission is exactly the opposite of what we learned about beta decay. So here it is. So a positron is being emitted from the nucleus, so a proton is turning into a neutron. So our mass stays the same because our total number of protons and neutrons stays the same, but our atomic number decreases by 1 because we've changed a proton into a neutron. And then lastly, electron capture. So this is different than the other types of radiation we've discussed so far because nothing is being released from the nucleus. Nothing is being emitted, right? This one, we have something being absorbed by the nucleus. So what happens is that an electron from one of the inner orbitals, one that's really, really low energy, one of those electrons can get pulled into the nucleus. And when that happens, right, when that electron gets pulled into the nucleus, a proton will combine with that electron and they make a neutron, right? Because the positive and the negative make neutral. Okay, so the mass number will stay the same because our total number of protons and neutrons in the nucleus doesn't change, but our atomic number decreases by 1 because we've essentially lost a proton because it changed into a neutron. Okay, so there is no particle that's being emitted here, but our nucleus still changes. Okay, this is actually going to end up being the same result as a positron emission. You would end up with the same product here. Okay, whether you underwent a positron emission or electron capture, they are different processes, but they end up with the same product. All right, so here's just a summary of some important atomic symbols we've talked about so far. Neutrons, right? We've talked about those a little bit. Electrons, we've got protons, alpha decay, beta decay, we've got positrons, all kinds of things. So this is just kind of a summary of all of them together. For protons, you can either write hydrogen or you can write a P. Either way is fine because we're not dealing with the electrons. Those are the same for our nuclear symbol. Same thing with our alpha decay and helium. Right? Since we're not worried about the electrons on the helium, we can use it as either alpha decay or helium. And then beta decay, you can either use the beta or the electron. Either way is fine. So here are a summary of the particle changes. So I've left off alpha decay and gamma emission because those aren't particle changes. This is when something is turning into something else. So like beta emission, we have a neutron that's changing into a proton. And then in positron, we have a proton that's changing into a neutron, right? Remember that those are opposite. And then electron capture is where a proton changes into a neutron, kind of like our positron emission, but it's happening in a different way. So this is just kind of to sum up so that you can really visualize those. And then here are all the different types of decay. So this has all of our decay modes. It's got our examples kind of in a picture, tells you how our mass is changing, how our atomic number is changing, and an example of where you would see that. So this is a really good summary slide just to keep all of it all together. All right, let's go through some examples. So this is our examples in pictures, and then we're going to look at examples in writing nuclear equations. So this asks what kind of decay is happening and how many protons and neutrons are in the daughter nuclide. Okay, so right now we're starting off with 11 protons and 9 neutrons. And over here, right, we've lost 2 protons and 2 neutrons, right? The protons are red and the neutrons are black. So we've lost 2 protons and 2 neutrons. That means we have lost a helium, okay? So if we've lost, 2 protons and 2 neutrons, that means we are going to be left with 9 protons and 9 protons and 7 neutrons. All right, let's try another one. So we started off with 9 protons, 12 neutrons, and we have lost an electron. And when we lose an electron, remember we're losing the electron from the nucleus, right? Not from the electron cloud. So we're losing an electron from the nucleus. That means that this is beta decay. And when we lose an electron from the nucleus, one of those neutrons gets turned into a proton. So now we're going to have 10 protons and only 11 neutrons. And then lastly, we're starting with 5 protons and 4 neutrons. So now, instead of losing an electron like in the last one, we are losing a positron. Okay, and remember, positrons are going to be the opposite of our electrons. So when we lose a positron, instead of having 5 protons and 4 neutrons, now we're going to have 4 protons and 5 neutrons. Because remember, in a positron emission, we are going to take one of our protons and it will get turned into a neutron. Okay, so let's write some nuclear equations. Remember, in the nuclear equation, we need to make sure that our mass numbers and our atomic numbers are conserved. And we'll use that to figure out the identity of the daughter nuclide, if we know the parent and the type of emission, or we might figure out the parent nuclide, we might figure out the type of emission, right? But we can use all of this mathematical relationship to figure out, what's missing. Okay, so let's go through an example problem. This says, write the nuclear equation for positron emission from potassium-40. So our first step is to write the nuclide symbols for both the starting radionuclide and the particle emitted. So here it is for potassium, right? So K40, potassium-40, means that the mass of that isotope is 40. Okay, make sure when you're doing these, you're not using the mass that's on the periodic table. The mass that's on the periodic table is the average atomic mass. It is the weighted average of all of the isotopes of that element. And it's usually going to be the closest to the most common isotope of that element. And that may not be the isotope that we're working with in these problems, because oftentimes the isotopes that we're working with are going to be uncommon because they are radioactive. Okay, so just keep in mind that don't use the mass on the periodic table for these. Use the mass that's given to you in the problems. Okay, so this is potassium-40, so that's why our mass number on the top is 40, and the bottom number is 19. That is the atomic number of potassium. And this says that we are undergoing positron emission, so it's going to be 0 mass, and it's going to be an E just like an electron, but it's going to be a +1 instead of a -1. Okay, so now we can go ahead and start setting up our equation. So anything that is going to be emitted is going to be a product. And if we have something that's captured, like when we do electron capture, that would be part of the reactants. That's a little bit more unusual. Most times we're just going to emit something. And here we're undergoing positron emission, so our positron will end up on the right-hand side of our equation. So we have our potassium is what we're starting with, and then we're going to emit a positron and something. And we need to figure out what the something is. So we'll figure out the mass number and the atomic number of the missing nuclide just by doing some math, right? 40, you can think of the arrow as being like an equals sign here. 40 equals 0 plus something, right? So the number on the top has to be 40 because it's 0 plus something equals 40. And then the number on the bottom, right, we have 19 equals 1 plus something. So 1 plus 18 will give us 19. Okay, so the numbers on the top have to all be equal, and then the numbers at the bottom have to end up being equal. And then we'll go to our periodic table, and we will figure out what is element number 18. And then element number 18 we see is argon, and so that will complete our equation. All right, I have some for you to try. Okay, so go ahead and you're going to pause here and try and do the nuclear equations for these problems. So you've got an alpha emission, beta emission, positron emission, and electron capture. And then you've got a bunch of different radioisotopes there. So go ahead, pause here, try these out, and then come back when you're ready to see the answers. All right, let's go through this. So alpha emission from uranium-238. So uranium-238, so we have our 238 on the top and our 92 on the bottom, right? If we look at our periodic table, we'll see uranium is number 92, and it's undergoing alpha emission. So this is our alpha particle, okay? So 4,2 helium. So we know the numbers on the top have to add up. So 4 plus something gives us 238, so that'll be 234. And then same thing, the numbers on the bottom have to add up. 2 plus something gives us 92, so that has to be a 90. We look, we see element 90 is thorium. And we saw this problem earlier. Beta emission from neon-24. So again, we'll write neon-24 on the left-hand side. We'll look and we'll see neon is atomic number 10, so that's where we find the 10 on the bottom. And then it's undergoing beta emission. So beta emission is an electron that's being released. So we'll write 0, -1, and an E. Beta emission is one that people often do wrong, kind of like positron emission. Make sure that you're doing -1 plus something, right? So when we do that, our atomic number is increasing. Remember, we're taking a neutron and we're turning it into a proton during beta emission. So we always need to see an increase in our atomic number. So our mass number will stay the same on the top because it has 0 mass, and our bottom number will increase by 1 because we're taking a neutron and turning it into a proton. That will give us atomic number 11, which is sodium. Next one, so we have positron emission from nitrogen-13. Okay, so it's going to be similar to the one above it, except that our electron is now positively charged, essentially, right? Our positron. So our mass number won't change because it has a 0 mass, but our atomic number will decrease by 1 because we're taking a proton and we're turning it into a neutron during positron emission. So we'll see that we'll get atomic number 6, and we see that that is carbon. And then the last one is electron capture. So when we have electron capture, that electron will go on the left-hand side with our, our beryllium here. So our beryllium is going to capture an electron from one of those, innermost orbitals, okay? And it's going to do that, and it's going to take a proton and it will turn it into a neutron. So we'll see our atomic number decrease by 1, but our mass number doesn't change. So 7 plus 0 stays 7, 4 plus a -1 gives us 3, and our 3 is lithium. So that's it for today's lecture. We covered a lot of ground. We talked about what radioactivity is in general. We talked about the discovery of radioactivity, which I think is really, really interesting. And then we looked at a bunch of different types of radioactive decay and saw how we can write these nuclear decay equations by starting with our, our parent nuclide and looking at our daughter nuclide. We talked about how the different types of radiation are different with their ionizing power and how you can, like I said, protect yourself from them. And we looked at how nuclear equations or nuclear reactions are different from our chemical equations, right? We're changing the composition of our nucleus instead of, messing with our electrons. So lots of ground that we covered today. I hope it's pretty straightforward though. You do have some practice problems in your chapter lecture worksheet to get some practice writing these nuclear equations. So make sure you're working on that. And as always, if you're having any problems or you get stuck, please send me your questions so I can help you out. I love to talk about chemistry, and I think nuclear chemistry is really, really interesting. So keep working hard, guys. And as always, I will talk to you guys next time.